All right, sweet. Well, let's jump in on this review. So if you go to this week's module and pull up, it should be the first page of the module, the proofs test review or the proofs review. There's actually, if you look at it, so if you take a look at it, it's actually just 6 problems that I have there. Again, as we go through this, you'll kind of see. So what we're doing is we're just reviewing. Again, I'm not reviewing some problem that you have to memorize. What I'm doing is I'm reviewing the styles of proof that we've gone through. And in doing those styles of proof, we're going to see all the definitions too, that we kind of made an emphasis on. So even, odd, prime, composite, divisibility, all that kind of stuff. So that's what you want to focus on in this. It's just more when you read a problem, first can you identify, can either, what do you call it? Can you identify what type of proof you're going to need to get through it, or at least figure that out? And then, what do you call it? Yeah, just focus on, are you comfortable with that style of proof and how to work through it, more than anything. So, I've graded most of y'all's homeworks. I haven't, it's only Monday, so I haven't got to y'all's 5.2 and 5.3 homeworks. But from what I saw in a lot of y'all's homeworks, y'all are pretty, like, y'all are mostly okay with a lot of the direct proofs, which is going to be a majority of the test. But the contradiction proofs were a good bit harder for y'all, but honestly, that's not y'all, that's everybody who ever takes this class. Contradiction proofs are just harder. So especially kind of figuring out sort of what you need and where you need to go to find that contradiction. That is really the hardest part of it. But yeah, beyond that, you guys are doing well. Like, honestly, so you did well with the direct proofs. You guys overall are doing well with the proofs. So anyways, so let's go through these and see if we can do, like I said, again, identify what type of proof we're talking about, and then just make sure you're comfortable working through that style of proof. So question 1. So 1 is asking us to prove the following: if a and b are any odd integers, then a squared plus b squared is even. So, and actually, I'm not gonna rewrite the proof up here, only because you have that in front of you on PDF anyways. But if a and b are any odd integers, then a squared plus b squared is even. So first, like I said, you kind of want to identify, what type of proof are we looking at, and what type of proof is this likely? Good, it's likely a direct proof. And notice that, a couple things that let you in on that. It's an if-then statement, where, especially you look at the hypothesis, it references some pretty basic definitions that we're well aware of, and it asks us to then take that and look at some construction and prove, in this case, that it's fits another definition that we're well aware of. So most of these proofs are going to be direct proofs. It'll, again, when we get to it, it's that'll be the smaller part of this is identifying where you can't do the direct proof, and you'll need a contradiction proof, or where you're going to need something like a, what do you call it, an induction proof. I will say one approach you can always take is assume that it is a direct proof and then see if you can prove it that way. And if you can't, then it's got to be one of the other types of proofs. But when we get to the examples that are contradiction and induction proof, we'll just kind of talk about some things that you might see there that are good tells that it is a contradiction proof or something like that. So anyways, but yeah, so this seems like a pretty standard Stoic direct proof. So you're going to assume the hypothesis and then build your conclusion. So we are going to assume, so we're going to suppose A comma B are odd integers. Assume those are odd integers. And that's our hypothesis. So suppose A and B are odd integers. Now from there, often, almost always, but maybe not, definitely not always, but almost always on our direct proofs. Once we introduce our characters and we introduce some quality about those characters, what do we tend to always do after that line? Good. We use that definition to kind of flesh out, in this case, what A and B are. And then you want to introduce the construction that you want to kind of make a proof about here, that you want to make some claim about. We're trying to make the claim that a squared plus b squared is even. So then you're gonna have to introduce a squared plus b squared. And then you probably guessed it, use your definition that use the definition that you just introduced to kind of plug stuff in and work it out from there. So hopefully, again, as you just kind of look at what you have to do here and you think about how you're going through the proof, not only does it jog your memory back to some problems that you saw out of these sections, but it really like connects and makes a lot of sense with these proofs that you did in 4.1 through 4.4 that you guys, like I said, you guys did mostly well on. Again, I'm not 100%, but in general, they all flow the same way. You suppose the hypothesis, then your hypothesis usually has a definition in it, and we can use that definition to flesh out, a little more detail. And then we introduce our construction, and we use the construction and the detail to work our way towards what we're trying to prove. All right, so I want to give you guys a chance to work this rather than just have me work it, because that won't help you, kind of learn from the problem, basically. So I'll pause, you pause, go ahead and work through this, and then we'll convene back and I'll go through it and just make sure you have all the right pieces. All right. Let's see what you guys got here. So suppose A and B are odd integers. So like we said, the next thing you want to do is just give some definition then, or get some detail then about A and B because of the fact that they're odd integers. So you might say, so A equals maybe 2k plus 1. B equals maybe 2m plus 1, where m and k are integers. That's definition of odd. And then, like we said, since we're trying to prove a squared plus b squared is even, let's introduce a squared plus b squared, especially again, since we have a and b already. So that's now a squared plus b squared equals, and then we can start to make some substitutions there. So that's going to be 2k plus 1 squared plus 2m plus 1 squared. Good. And then we got to start working from here. So as I was writing this did remind me. So this was one of your homework questions, by the way. So I do remember on this particular question, and I think this is one of the reasons I highlighted this in the review, because so I think every semester I kind of see a little bit of the same thing. But anyway, so one of the things that I did remember was, again, you guys overall did well with these direct proofs, but one, I would say, semi-consistent struggle, honestly, was just some basic algebra skills. And I don't say basic to basically try to like naysay you guys or shoot you guys down, but I will say that something like fleshing this out, 2k plus 1 squared, 2m plus 1 squared, some people didn't even really do the squared. You just kind of multiply by 2. That didn't happen often, but that was a little bit. And then just some people really, they did the squared, but they really didn't do the result correctly. So you just didn't do the algebra correctly. So that is a total, so that's just something to work on when you're looking at this review. just kind of, reach back and make sure you can do all the types of algebra you see on the review. All the types of algebra we see really this is college algebra. These were skills that you learned in college algebra. And I'm not saying, I know a lot of you guys are different majors. Um, and so I'm not saying that you need all those skills every day. But those skills are the heart of any math class. So again, whether you're coming into this class from some really advanced math class or calculus or something like that, these are the basic and heart like skills that are at the heart of any math that you're going to do. So just kind of reach back and look if you looking at if you look at your grades on your homework and you do see that you were knocked off, I knocked off credit because of your algebra skills. I try to put comments on the homework so you'll see. I probably would have physically said that there was something off with the algebra. Just so if you see that, just make sure you go back and yeah, just get comfortable and know that you are comfortable with some of these algebra skills we're about to do. So yeah, this particular problem in particular, there was some consistent mistakes with the algebra, I guess. So 2k plus 1 squared, that's going to be 2k plus 1 times 2k plus 1. When you multiply that out, I will say though, I'm not going to write it all out only because at this point for a class like this, it is not only do I expect it, but it is a right expectation that you should not have to see the algebra. And now I'm not saying, again, if you were making mistakes with the algebra, as I'm writing this up here, do the work to the side and make sure you get to the same place. But I won't write out all the algebra because that is, again, that's just a basic skill, not just for this class, but for any math class. So 2k plus 1 squared, 2k plus 1 times 2k plus 1, that is going to be 4k squared. That is going to be plus 4k, and that is going to be plus 1. And then we're going to do the same thing for the 2m plus 1 squared. 2m plus 1 times 2m plus 1, that is going to be 4m squared plus 4m plus 1. I saw a lot of people that ended up with 2s here, or that were trying to force these to be 2s because you knew by the end it had to be even, but you didn't have to force these to be 2s. So for 1, I mean, when you multiply these out, these are a 1. You can't get any other result there. But also you're gonna end up with 2 1s, which means in total what I'm looking at here is 4k squared. Actually, I can let's even simplify it even more. So 4 k squared plus m squared plus 4 k plus m, and then it's going to be plus 2 at the end. Now, I'll be honest too, you didn't have to show me all of this simplification. So I mean, most of y'all didn't do any type of factoring out a common factor here. But the key is to realize this is a 2, 1 plus 1. So then we can factor out a 2 from all this. So my goal ultimately is to show a squared plus b squared is even. Remember, the definition of even is 2 times an integer. So the other small mistake I saw on this was several people kind of got here and then basically tried to make some comment about 4 times an integer, or show that this is 4 times something and therefore it's even because 2 divides 4. But that's not our definition of even. So I think sometimes the hard thing is, again, our intuition and our basically arithmetic and calculation and, like our tools in math classes you've had before this becomes actually a little bit of a roadblock to proving these things because you make it more complicated than it needs to be. Our definition for even is 2 times an integer. So no matter what work I'm doing here, my goal is to see 2 times and then a bunch of stuff over here that I can say is an integer. But ultimately, it's very simple. I just need to see 2 times a bunch of stuff. And so notice that this is a 4, this is a 4, this is a 2. I can factor out a 2 from all those. So yeah, so I'm going to factor out a 2 from all of them. And that's going to leave me with 2 k squared plus m squared plus 2 a plus m plus 1. And again, you could have left these undone. This could say 2 squared, 2k squared plus 2m squared plus 2k plus 2m plus 1. That doesn't matter. That doesn't bother me at all. Again, my goal when I was grading this was to see the correct algebra, and then for the algebra at the end to show that this was 2 times something. Because then once you have that, we almost have the definition of even. I just need to show that this something is an integer. And it is. Why is this an integer? Good, because the sums and products of integers are integers. So we can make this whole thing this is an integer because sums and products of integers are integers. Once I've said this, what I have is a squared plus b squared is 2 times now an integer, so I can say therefore a squared is b plus b squared is even by the definition of even. And that is our proof. Again, just this is the direct proof. Like I was talking about to begin with, it's hopefully not, I won't say easy is not the right word, but hopefully it just kind of stands out to you. It's pretty comfortable for you to see that that's easily a direct proof. If then with simple definitions. So we suppose the hypothesis, give some details based on the definitions that are talked about in the hypothesis, introduce our construction, and then in this case, because it's a pretty algebraic claim, we kind of let the algebra do the rest of the work from there. Good. All right, let's look at another proof. This one is saying on 2, we want to prove for all integers k greater than or equal to 4 that 2k squared minus 5k plus 2 is composite. And so this was either the exact proof that you guys did for homework, or again, I probably just modified the number and the expression just a little bit. But it's exactly like one of your problems in your homework. So let's look through this. Now notice this doesn't naturally read as an if-then statement, but you can think of it as an if-then statement. So we're saying if k is greater than or equal to 4, then 2k squared minus 5k plus 2 is composite. So, and if you can think of it as an if-then statement, then if it is a direct proof, then you've got your exact, you know where to start and you kind of know where to go from there. So then what would be the start on this? What's the suppose on this one? So we might say something like suppose. So again, the if here is if a is an integer greater than or equal to 4, then 2k squared minus 5k plus 2 is composite. So suppose k is an integer and k is greater than or equal to 4. And that's actually all my hypothesis is. So I think the one weird thing about not just this problem, but sort of this type of problem when you guys were looking at it in the homework was it's not saying anything then about k being even, odd, and even it doesn't even actually say that k is composite. It just says it's an integer greater than or equal to 4. We need to get to the fact that that construction is composite though. So I guess what I'm trying to say is notice that this is, so far we got a good start to a direct proof, but there is no definition to kind of give more detail about k from here. So that means I want to go straight to my construction. I want to start with 2k squared minus 5k plus 2, and I need to show that the factors of that. So we want to think about what composite means. So what does composite mean again? Good. I want to show that the factors of that are, one way we did this was basically as long as those factors are greater than or equal to 1, then it's composite. Because if it's composite, that means at least one pair of my factors is not 1 in the number itself. So that means at least one pair of my factors is greater than 1. So that's where we want to go with this problem. We want to introduce the construction and we want to show that the factors somehow are greater than or equal to 1. And so I mentioned this in the last lecture, but also saw this, I saw this a little bit when I was grading. So I think a lot of people did pretty well with this problem on the homework or this type of problem. However, some people did struggle because I could tell you kind of didn't know where the inequalities come from. So you would make some general statement about once we get to, once we see the factors here, that the factors somehow are greater than or equal to 1, but you didn't really show why they were greater than or equal to 1. So I think the slightly odd thing about this problem is, again, this is all I got for my hypothesis, but notice that I have an inequality. This inequality is the key to this problem. Because we've got to show that my factors are greater than or equal to 1, which means I need an inequality to start so that I can actually make the claim that my factors are greater than or equal to 1. So you unfortunately can't just say that they are, or they should be, or it seems like they are. You got to show definitely that your factors are greater than or equal to 1, which means we need an inequality to start out. Anyways, so this will come back when we look at the contradiction proof, or maybe not that contradiction proof, but this came back when you guys looked at contradiction proofs in chapter 4.7. I noticed this a good bit actually. So when you guys did the contradiction proofs, a lot of people had trouble kind of figuring out what inequalities to use. So we'll, what do you call it? I don't know, in those proofs, sorry, I'm kind of all over the place, but I guess I'm trying to address all the things that I remember seeing kind of as I went through the homework. So in contradiction proofs, often your inequalities come from some basic inequality, like 1 is less than 2 or something like that, and then you build it into the expressions that you assumed were true. For a direct proof like this, in order to prove something with an inequality, you need to start with an inequality, and we do. So anyways, so I guess I'm saying all that to say this inequality is key, and we don't need definitions. So you'll see with this proof, we actually don't need, like we did on the last proof, we don't need to write out anything about K or the construction, like it's even or odd, and we have a definition. We don't need any of that. So sorry, I think I'm rambling at this point. But okay, so we are trying to prove this directly. This is my hypothesis. I'm going to introduce my construction. So now 2k squared minus 5k plus 2. I need to say something about the factors of this, which means I need to factor this. So that's the first thing you need to do is to be able to factor a polynomial like that. So again, that's another algebra skill that, again, I'm not going to sort of remind you how to do it or kind of like, but I just make sure after you're done looking at the review that you're comfortable doing that not just this factoring, but any factoring. That is a basic skill that, is an integral element of any math class you're ever going to come across. So I'll give you guys a second. I won't even pause, but I'll just give you guys a second to go ahead and factor this. All right, and let's see what you got. This should be 2K times K. And that should be what, -2 there and -1 there. And then, like I said, so this is where I think I was just, I was talking in circles instead of, I should have just wrote this up there. But this is where I'm kind of mentioning that we've then got to show that these factors are greater than or equal to 1. But the only way to do that is to actually prove it with like from an inequality. You can't just say that they should be or they are. If you can write the words, if you can write the words involving k greater than or equal to 4, then sure, you can write it out. But otherwise, you need to use an inequality to show an inequality. So again, this came in play into your contradiction proofs in 4.7. You needed to use an inequality to show an inequality. You couldn't just say, for instance, in 4.7, quite a few of you said, oh, well, m divided by 2 has to be, or n divided by 2, whichever you used, has to be greater than m. But it doesn't have to be, or at least that's not a proof. That doesn't prove to the reader or prove to me that it definitely has to be. You're just saying it has to be. So that was meant, to say one thing is greater than another, that's an inequality. So to prove an inequality, you need to start with an inequality. So we'll do the same thing here. I need to prove that these are greater than or equal to 1, so I'm going to start with an inequality, and that inequality is the one I already have in the problem, k greater than or equal to 4. So I can say since k is greater than or equal to 4, then notice that if k is greater than or equal to 4, then I literally can sort of just plug in k here and, effectively. So the idea, at least mentally in your head, is you plug in k here and you can figure out what these have to be greater than. So then 2k minus 1 then would have to be greater than or equal to 2 times 4 is 8, minus 1 is 7. So 2k minus 1 has to be greater than or equal to 7, which is definitely greater than 1. Sorry, not equal to 1, but greater than 1. And honestly, you almost don't even have to say that. I know as a reader, if it's greater than 7, it's greater than 1, but you'll see kind of for the flow of the proof, it actually makes it nice to see it written out so that when we get to the definition of composite, the reader kind of understands where that's coming from. So 2k minus 1 is greater than or equal to 7, which is obviously greater than 1. K minus 2 is greater than or equal to 2, which is also greater than 1. So I've shown that both of my factors are greater than 1. And that is my definition of composites. Therefore, 2k squared minus 5k plus 2 is composites. And that's definition of composites. And that's it. We've our conclusion. We've gotten to the conclusion. We've gotten to what we were trying to prove, which is that this construction is composite for every k greater than or equal to 4. Good. And that would be the proof for 2. So then taking a look at 3, 3 says for all a, b, c, and d, and that are it's basically for all integers a, b, c, and d. Notice here again, I write out the if-then statement for you. So if a divides c and b divides d, then I want you to prove that ab divides cd. A second. All right, so again, you have a nice kind of if-then statement. So this should be a direct proof. And so again, notice that, like I said, because whether I write the if-then statement out for you, or you can write that out for yourself or read it in you kind of say it in your head. Once you have the if-then statement, the if is where you start, the then is where you go. So this one, I won't even, last two, I kind of wrote the supposed part of it. So I want to give you a chance to just go full bore from beginning to end on it. Suppose all the way down to therefore. So I'm going to pause, go ahead and pause yourself, and then see if you can write a direct proof for this. Blow me away. Oh, sorry. All right. All right. So let's take a look at through there. All right. So we needed, again, you needed to suppose, you needed to start with your hypothesis. So we're gonna suppose, and we could just include all this stuff. A, B, C, and D are integers such that A divides C and B divides D. Good, so that's our hypothesis. Now, the fact that A divides C and B divides D, that's definition of divisibility, so I can give a little more detail there. Let's see, suppose that then C is going to equal A times, let's say, R. D is going to equal, not A, B times maybe S. R and S are integers. And this is the definition of divisibility. Good. Good. So then, looking at the rest of this proof, so usually, right, there's a construction that we have to put together. And notice that our goal here is to say that AB divides CD. So we want to show that our goal is to have AB times an integer equals CD, which means our construction here is, I feel like in this problem, the construction isn't as obvious, but we still have kind of the same approach. I'm going to construct CD. I want to show that CD is actually just AB times an integer. So I need to introduce that product into my proof, into the world of the proof. So now CD equals, so that's where we wanted to go next. CD equals, and using a little bit of substitution here, that's going to be AR, BS, that's substitution. And then my goal is then, so the nice thing about this is now I have CD equals the product of a bunch of integers on the right side. So number one, that's nice. And that starts me towards the definition that I'm trying to prove. And it also gives me the A and the B. And again, what I want is AB times an integer equals CD. So let's just do a little rearranging here. So using a little bit of algebra, this is going to be AB times RS. Now, is RS an integer? So, because now I almost have it. I have AB times something. Is RS an integer? Good. Of course it is. So RS is an integer because of the product of integers. So now and RS is an integer because it's a product of integers. And then we got it. So we got CD equals AB times an integer. That is the definition of divisibility. Therefore, AB divides CD. definition of divisibility. And we got our proof. Good. All right, let's keep going. The next one, 4, you have to prove that the product of any two rational numbers is a rational number. And so the part of this is again to test. So another key definition very key definition, honestly, that you should have is what a rational number is. And I want to make a distinction too, we'll see, between this proof and the next proof. So this one, again, so the first thing you want to think about is, can you think about it? Well, sorry. I want to kind of make a call, on the type of proof that you're going to use here. And if we can think about it as an if-then proof, then we can probably prove it directly. So could you rethink of this, or does this read, can this be rewritten as an if-then statement? And good, it can. So it says the product of any two rational numbers is a rational number. So we could say if such and such, whatever we wanted to say, but if maybe A and B, I don't know, X and Y, I guess it doesn't matter. If R and S are two rational numbers, we're saying then the product is a rational number. So this can be recoded, rewritten as an if-then statement. So if R and S, let's say, are two rational numbers, then the product is a rational number. Good. And we're dealing, we're dealing with rational numbers. So we should be able to then do this as a direct proof. So again, this first part, oh yeah, sorry, I'll just leave it as what we already said. So this should be a direct proof. So then you got to suppose, okay, yeah, that applies to the other proofs. So I think, again, I just sort of want to, I was kind of talk through how to rewrite it as an if-then statement. Again, this is not something you have to put in the proof, but I just want to write up what I said there so that we can get a good start on this. So if R and S are any two rational numbers, then their products I mean, it is that, but let me just be simpler about this. Then their product is rational. Oh, man. Product is rational. So again, the way it's written is kind of the more informal way. This is a little more formal way to say it. But either way, we're saying as long as I've got two rational numbers, when I multiply them, I get a rational number. So this gives us our start then. We can suppose this and then work towards their products being rational. So same deal. Go ahead and pause, and I'll pause, and then see if you can put this one together as well. Let's see what you guys got. So we're gonna start out supposing the hypothesis. So suppose R comma S are excuse me, rational numbers. And so then, like all of our other direct proofs, the fact that I know R and S are rational numbers, I can then use that definition to give some detail there. In other words, R equals A over B, S equals C over D, and then the usual stuff. So A, B, C, and D are integers. The bottoms, so B comma D don't equal 0, and this is all definition of rational. Now, again, my goal for this is to see that the product, so I want the product of these two things and to see that the product is rational. But again, the fact that I want the product, that's the construction. So that's the construction I need to introduce. Now, and I will say from y'all's homework, so y'all didn't actually struggle with this too much, but I did see a small tendency to, again, so something like this, it's kind of like what I saw people doing is kind of doing the product and trying to say something about a rational number divided by an integer or something like that. And just remember that your goal of the problem is to show that this product is rational, but just like we talked about for that first proof, it's just to show that it's rational, and rational has a definition. So that's all I ever need to show about it. I don't need to make sort of a calculation argument, an arithmetic argument. I don't need to like appeal to the reader with some sort of intuitive argument about what it should be, because ultimately none of those are actually proof. None of those are accurate arguments that it's rational. Rational means I need to show that this thing is an integer on top, integer on bottom, and the bottom isn't 0. So the rest of my proof should only be bent towards that. It should only be mentioning that, because that's the only thing that shows that it's rational, because that's our definition of rational. So what that does, though, you'll see when you're writing these proofs and when you look over this for the review, what that does, though, is it actually makes the proof much simpler than I think. Again, so like I said, it wasn't everybody, it wasn't even a lot of people, but some people sort of had this tendency to, like, again, appeal to sort of these intuitive arguments or try to make this like, if it's this, then it's this. And the thing is, that's actually too much. It's too hard. It's too strong. You're kind of doing too much for what you really need to do. So again, if you just try to serve the definition, make the end goal your definition, that actually makes the proof much simpler. So I'm just going to multiply an R and S, and I'm going to do some substitution here. And then I just got to show that whatever the result is an integer on top, integer on bottom, and the bottom doesn't equal 0. So it'll be certain, very specific, fine-tuned, clear points, and then I'm done. I got it. So RS then is going to be A over B times C over D, which equals AC over BD. And again, the nice thing about this is that it's simple from here. I just need to show AC is an integer, BD is an integer, and BD doesn't equal 0. So I will then say that AC and BD are integers because they're products of integers, and we know products of integers are integers. Products of integers are integers. And then I also need to show that the bottom doesn't equal 0. And how do I know that the bottom, that product BD doesn't equal 0? Good, so here's where the other kind of one of our, not necessarily, well, one of our assumptions, but one of our assumptions that we need to use often in proofs like this, anything with rational numbers, is we know to begin with that B and D don't equal 0. So we also then know that if I'm multiplying two things that don't equal 0, my product can't possibly equal 0. But that knowledge or that pattern, that property is called the zero product property. So by the zero product property, I know, let's see, and BD doesn't equal 0, and that's the zero product property. But once I have that, I have my definition. The top and the bottom are integers, and the bottom doesn't equal 0. Therefore, RS is rational, or you can say the product is rational, and that's just by the definition of rational. And you got it. That's your proof. All right, good stuff. All right, so let's jaunt on to the next proof. Now notice the next proof, and actually, well, yeah, we'll talk about that. I guess I didn't leave a word out of there, but we'll talk about sort of something I could have written in there that I didn't. But number 5, I'm asking you to prove that the reciprocal of any irrational number is irrational. This was also one of our homework problems. Notice, basically just notice the word irrational. So when we were looking at section 4.7, I made kind of a comment, huge comment several times, that one of our main uses of a contradiction or a contraposition proof is to prove things that involve definitions where the definition isn't really a definition. The definition is just saying it's not some other category. And irrational is exactly that. There is, when the definition of irrational is not like rational, where it's saying it's this and it's that and it's, has these conditions. The definition of irrational is just not rational. It's just not that thing. Can't be represented that way. So because of that, so anytime you're dealing with a definition that's like that, I guarantee you guys that is a contradiction or a contraposition proof. So we can go contradiction. And again, the strategy there is we're gonna assume the negation of it, and then from there kind of derive a contradiction. Or you can do the contrapositive proof, the contraposition proof. And we can do the contraposition proof because when you do the contrapositive, what you do is you take the if-then statement that this would be, and you flip it around and then negate it. And so again, you're dealing with a negation. So basically, whether you're doing contradiction or contrapositive, the reason these proofs work for things things like irrational numbers is because in essence, what you do in either proof is you negate that irrational and turn it into talking about something rational, which is then something we can actually deal with. That's a definition we can deal with. We can confirm that something's rational, just like we did on this proof we just finished. Good. So that's a good tell that you're looking at a contradiction or a contraposition proof. I don't want to go through both options here, I will say, more because of time than anything else. But I know this proof in that section had you do it as a contrapositive proof. So give me a second. So I think what I'll do is, since you guys have that homework, so the contrapositive version of this proof, I basically want you to look at your homework for that. And so one comment then on your homework, when you guys were doing this proof on the homework and you're doing the contrapositive, excuse me, what I saw from a couple people was when you did the contrapositive statement, you flipped the order, which is the converse, but then you didn't negate each part. And so you ended up with kind of running into a dead end of the proof, and it was actually just because you didn't negate each of the parts of your if-then statement. So remember to do that for contrapositive. Again, that was the reason for studying, for hammering that and kind of making, like doing that so much in chapter 3 and chapter 2, was so that then when you see something like this, you are completely fluid with making the contrapositive. So contrapositive means you flip the if and then the if then statements, or the two parts of the if then statement, and you negate each part. So I think what I want to do is I want to leave the homework, leave what you did on the homework as kind of your example for this as a contrapositive proof. Since we didn't do a contradiction proof for this in the homework, I think we'll do a contradiction proof for the review. Second to. Man, my head really hurts right now. All right. Not going to be easier than maybe just folding into. No, it's going to be the same thing either way. Yeah. Okay. So we're trying to prove the reciprocal of any irrational number is irrational. Again, your homework, you can look at that for the contrapositive version of it. We'll do the contradiction. Again, by the end of this, though, when you're looking at this on the review, I want you to go with whichever way you're most comfortable with. So part of this is just to get you to practice a contradiction proof, but then you get the decision whether you're comfortable more with contradiction or contraposition. So then on the test, that'll again, what do you call it? You'll have that option. You can do either of them, and in general, both of them work on the same statements. So the reciprocal of any irrational number is irrational. To do a contradiction proof, you first got to suppose the negation. So the first thing is we want to write down, or you want to think about what the negation is. So what is the negation of this statement? So my original statement is saying for all the irrational numbers, if I take the reciprocal of it, I get an irrational number. Okay, fair enough. So the negation of that then, again, that's a for all statement. So the negation of that, first of all, has to be a there exists statement. So we're saying there exists some irrational number. So remember, so basically when you do the negation of this, you're doing the negation of an if-then statement. And the negation of an if-then statement is you keep the hypothesis and it's an and statement. So hypothesis and the negation of the conclusion. So the negation of this is going to be there is an irrational number. So it's still, what do you call it? Yeah, there is an irrational number whose reciprocal is rational. So again, there's that negation. You're negating the conclusion there. So I'm gonna, again, this doesn't have to be part of your proof, but I'm just gonna write this down here so we see it physically on the board and kind of have a framework to go forward with. So the negation of the statement in 5 is there is an rational number x whose reciprocal is rational. And again, just as a small note, this is why, again, in chapter 2 and chapter 3, not just her, but I made a big deal about having you guys do a lot of negations and really correcting you on, how to do the negations for an if-then statement, because that's the name of the game when we get to a contradiction proof. You have to be able to negate that original statement. So there is an irrational number x whose reciprocal is rational. Or again, we're just making the opposite claim. So the original claim is every irrational number, you do 1 over that number and you get an irrational number. The negation is, wait, hey, hold on. There is one. There can be only one. No, not there can be only one. But there is one. They do exist. Sorry, a bunch of old references. But there is one irrational number that when you flip it, actually you get a rational number. So, but this then provides the framework for a contradiction proof. So you're going to suppose. So we always start a contradiction proof. The slight weird thing about it is you start out supposing not the hypothesis but the whole statement. So we're going to suppose that this is true, and then we're going to use the fact that it's true and whatever might come out of that to work our way to a contradiction. So you want to start out supposing all of this is true. So suppose x is an irrational number. Suppose x is an irrational number and the reciprocal 1 over x is rational. Now, one thing that, so when I was kind of looking at y'all's proof for this, even the contrapositive version, there's one fact that it mentioned it in the book, but there's one fact that it's one of these that's obvious, so it doesn't need to be said in the formulation of the proof. Or sorry, it's not said in the statement of the proof of what you're trying to prove, because they assume it's obvious to the reader. But it's something that I want to make a point to bring up here because you will end up needing it in the proof. So something that we're going to state to the reader that maybe is obvious, but just in case it isn't obvious. So whenever you're dealing with something like reciprocal 1 over x, you want to make sure, obviously, so what's the one number that x can't be here? Good, x can't be 0. So by stating that we're dealing with 1 over x, we're implying that x is not 0. And so we can just assume that the reader knows that, but we might want to make mention of that. Another way we know that it's not 0 as well is that we say, suppose x is an irrational number. Well, 0 is a rational number. So by saying that x is an irrational number, I've already said, I've again intoned that it can't be 0. But I might want to make that point then. So x can't be 0. Actually, sorry, maybe we need that for the contrapositive version of the proof, but maybe we don't need that for this version of the proof. Yeah, maybe we don't need that for this version of the proof. Well, I think, okay, so it will, I guess it will come into play for this proof. You needed it also in the contrapositive version of this, but so we know x doesn't equal 0. And again, I think maybe this is obvious to the reader, but maybe not. So it's irrational, so it can't be 0. Also, you're doing a reciprocal and you can't divide by 0. So x can't equal 0. That's fine. And we've said that 1 over x is rational, which means now we have a definition that we can play with again. So like I was saying, the purpose of doing the purpose of doing either a contradiction or a contraposition proof is the fact that you're negating, because negating turns one of our definitions, one of our irrational numbers here into a rational number, and a rational number is something with a definition that I can give details to. So x obviously doesn't equal 0. And 1 over x then is rational, so I can say maybe it equals a over b with the usual parts to my definition. So a, b, b's are integers, b's integers. B doesn't equal 0. Definition of rational. So then, like I said, so that's good. So now we have some details. Now the funky thing about a contradiction proof is you kind of have to meander yourself into a contradiction. Now, the fact that 1 over x equals a over b means that I can do some algebra here and basically isolate, kind of get x by itself. So then, or go on. Say by algebra. And let's make it pop up right underneath here. Then x is going to have to equal b over a. And that the reader can easily confirm with their knowledge of algebra. And notice that since x can't be 0, then, so if I'm assuming that this is what x is, then a can't be 0. Or sorry, b can't be 0, not. I'm sorry, guys. Maybe it just really doesn't come into the contradiction version of this proof. We do have to say that x doesn't have to equal 0, but this isn't exactly the reason. So give me a second. Let me just figure out how this fact works in the contradiction version of this proof. Yeah. I got it. Sorry, y'all. So we do need the x doesn't equal 0, but the reason we need it is once, so when we're looking at 1 over x, we also need to know that 1 over x is not 0, because again, where we got to get to is a doesn't equal 0. So even in the contrapositive proof that I saw you guys do on this one, you did a pretty good job with the proof, but a lot of y'all missed that a can't equal 0, and so that's kind of the rub here. So before Yeah, maybe basically just save that for the next line. But okay, so x doesn't equal 0, 1 over x equals a over b. But if x doesn't equal 0, 1 over x can't equal 0 either. So x, I'll be cheap here and just say, so 1 over x doesn't equal 0, which means a can't equal 0. Because if 1 over x is a rational number, the only way for it to be 0 is for a to be 0. So now we can say something like we were saying before. So now by algebra, x equals b over a. And notice that now x is an integer divided by integer, and the bottom integer doesn't equal 0. So you can say something like, but that means x is rational. There, again, our definition of rational. And that's our contradiction. X cannot be both rational and irrational because they literally are complements or negations of each other. They're literally a 1 is 0, a true and a false. And once we have that, that's our proof. All right, so then let's get through the last one. I needed to be out of here about 20 minutes ago. But let's finish through this. Let's see. All right, so then let's look at 6. But again, the fact that it was talking about irrational, so again, some definition where it's just a negation of something, some actual definition with some real conditions, that's your tell for contradiction or contraposition. Then this last proof that I gave you, notice that, so I'm asking you to prove for every integer n greater than or equal to 3, that 4 cubed plus 4 to the 4th plus 4 to the 5th, all the way to 4 to the n equals 4 times 4 to the n minus 16 over 3. And again, I think this was one of your homework problems. Good. But notice that this is a, what do you call it? This is a, on the, so in a, there's an equation as a statement that you have to prove. And the left-hand side has a sum there. So we saw in section 5.2, that's a telltale sign of an inductive proof. Now in 5.3, there was some things we proved that didn't necessarily have an equation. There are statements that weren't necessarily an equation, especially an equation with a sum on one side of it. But they still usually would say something like for integers n greater than or equal to 3 or k greater than or equal to whatever. So that's also not a definite telltale sign, but a good sign of inductive proof. So the reason I say that, just looking at the fact that it says n greater than or equal to 3, that's not necessarily a sign of inductive proof, because if you look back at problem 2 on this review, it said k is greater than or equal to 4, but that wasn't an inductive proof. So again, so you don't want to, that's not the definite one, but if you see a statement like this, or if you see some other statement paired with something like n greater than or equal to 3 or whatever, that you can't seem to prove with a direct proof, then that is an inductive proof. So the key here is, this is an inductive proof. And so to make an inductive proof, what we just looked at last week was that statement that you're trying to prove. The nice thing is you don't actually physically have to prove that that statement works. What you do is you prove that the base case works, the first version of that statement, and then you assume that the kth statement works, and we call that the inductive hypothesis. And then using that hypothesis, we try to prove that the k+1 statement works. And if you can prove that little causation, that little if then all of the statements work. And that's all we need to do. So let's see if we can get that going for this one. So I want to start out just by defining my statement. So let P of n be the statement 4 to the third plus 4 to the fourth plus 4 to the fifth plus ... 4 to the n. So basically what I'm looking at is I'm adding up the powers of 4, starting at 3 all the way up to whatever n is, and up to. And if I do that, the claim is that number is exactly just 4 times 4 to the n minus 16 divided by 3. So that'll be my statement for P of n, n greater than or equal to 3. Good. So then to start making like I said, to start making the inductive proof, we got to start with the base case. So we got to start with proving basically, so the base case here. So you got to think about, first of all, what's my lowest integer that I can use here, and what's the lowest integer here? Good, that's 3. So the first thing I got to do is try to prove the P of 3 statement, or just show that the P of 3 statement is true. Good. So again, let's see if you can do that. So I want to give you guys, go ahead and pause on your side. I'll pause on my side. We'll take a second. See if you can show the P of 3 statement. All right, so the P3 case. So we basically, again, we gotta show that the left side and the right side match, that they're equal. So we might do something like this. Let's start with the 4 times. So the right side of this is gonna be 4 times 4 cubed minus 16 over 3. So if you do a little bit of the work there, 4 cubed is 64, minus 16 is a 48. So this is 4 times 48 over 3, which is 64. And as well, 4 cubed is also 64. So this checks out. The left and the right side match each other. All right. So then we want to, so once we got the base case, we want to do the inductive hypothesis. So we want to assume, so suppose this is true just for k. The kth case is true. So suppose 4 cubed plus 4 to the fourth plus 4 to the fifth, all the way up to now 4 to the k power. That equals 4 times 4 to the k minus 16 over 3. And then what we want to do is take what we have so far and basically we want to see if we can build or prove the k+1 case. So here we go to the inductive step. And by the way, so k is an integer. K is greater than or equal to 3. So now we want to look at the inductive step. And so I want to show the k plus 1 case, which again, I'm just going to imagine this in my mind. But the k plus 1 case would be 4 cubed plus 4 to the 4th plus 4 to the 5th, all the way up now, not to 4 to the k, but to, we're going to add on 4 to the k plus 1. And that should equal 4 times now 4 to the k plus 1 minus 16 over 3. So as we did on a lot of these proofs that involved addition there, what I'm going to do is I'm going to introduce the left side of this, but with the 4 to the k plus 1 added, and then we're going to see if both substitution and algebra gets us to what the right side should look like. So I'm going to start out now 4 cubed plus 4 to the 4th plus 4 to the 5th plus dot 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 all the way up to the 4 to the k plus 1. Wrote it wrong. Oh my goodness. Well, what we can say is that that equals 4 cubed plus 4 to the 4th, etc. That equals that up to 4 to the k, then plus the 4 to the k plus 1. But this part, the 4 cubed up to the 4 to the k, we already know equals this. So I'm going to use some substitution and replace this. So we're going to have 4 times 4 to the k minus 16 over 3 plus now our new 4 to the k plus 1. And so from here, I actually don't have as much room as I'd like to show all the algebra, but here we have to do some good algebra with fractions. So I am going to sort of take this all the way back here so that we have enough room. So the first thing I'm going to do is I'm going to make both of these fractions. So I'm going to put this, the 4 to the k plus 1, I'm going to make it so that it's 4 to the k, so that we have over 3 in the denominator. So that's easy to do, just multiply it by 3 over 3. I'm also going to do some work here. I'm going to multiply through by the 4 on top. So a couple steps in one there. So if I multiply through by 4 on top on the fraction on the left, that gets me 4 to the k plus 1. And that's minus 64 over 3. Then on the right, I'm going to turn that into a fraction by multiplying it by 3 over 3. So it's going to be 3 times 4 to the k plus 1 over 3. But I'm doing that for a couple reasons. So ultimately, I want to be able to add these two fractions together because I know that my 4 to the k plus 1 statement, the right side of that statement should be this, except for instead of k, it's k plus 1, but it should be one fraction. So whatever I have here has to end up becoming one fraction. So I make a common denominator and I multiply this stuff out so that then we can start combining what we have there. So notice that we can combine. That's going to be over 3. And notice we have some tricky, clever, but also curious and kind of what makes this work algebra here. So here we have 1 4 to the k plus 1, and notice I'm going to be adding 3 4 to the k plus 1s. And one of them plus 3 of them is 4 of them. So this combines to 4 times 4 to the k plus 1 minus 64. Now you could multiply through, so kind of going to the next step, I could multiply through by the 4, but again, I got to think about my goal. My goal is actually a fraction that reads 4 to the k plus 1 minus 16, so reads this in the top, but 4 to the k plus 1. So notice I kind of already have that, or I'm kind of close at least. I have 4 to the k plus 1, but it's times 4. And so instead of 4 being outside of parentheses, it's kind of tagged onto the 4 to the k plus 1. And instead of a minus 16, I have a minus 64. But it looks like I can get there because I can factor out a 4 from the top. And if I factor out a 4 from the top, that kind of factors the 4 that we have here to the left. And so we're left with 4 to the k plus 1. But then negative 64 divided by 4 is a negative 16. And voila, I have the right side of the 4 to the k plus 1 statement. So therefore, p to the k plus 1 is true. And again, once you have that, you have the whole proof. Yeah, so P of 3 knocks over P of 4. P of 3 means P of 4 is true, means P of 5 is true, means P of 6 is true. Again, only because I can show that in general, which whatever K is, P to the K being true means P to the K plus 1 is true. And I've got it. All right, good stuff. So that'll get you guys set up for this test. Again, your proofs, the proofs are going to be the same types of proofs, just obviously saying different things. So again, don't try to memorize these, but just be comfortable with the types of proofs that you're doing and how to work through them. And I guarantee you, if you got that, then you got the test, because I'm just going to give you some direct proofs, mostly direct proofs like you saw this for this review, but I'm going to give you some direct proofs, some contradiction proofs, and some inductive proofs. All right, so I'll be sending back, if you haven't replied to the message I sent out last week, I ended up sending it last Friday about the time slots. Go ahead and do for the test this week, go ahead and do that. And I'll be sending out those links probably tomorrow, honestly, so at least tomorrow and Wednesday. And otherwise, I will see y'all when you zoom in for the test.